As you know, in every IAC, we have the last session of the late breaking news, which deals with the, as it says, the late breaking news regarding to space exploration or something that happened somewhere in the universe. Mainly, the late breaking news related to missions that we know that something will happen, like last year we have the Rosetta, this year we have the New Horizon, the Dawn, and still the Rosetta. But we have a very good luck that 2 or 3 weeks ago, NASA confirms existing of running water of the surface of Mars. As you know, finding extraterrestrial life somewhere in the solar system or the universe is a dream that I think we are dreaming hundreds of years. On the late 19th century, Schiaparelli thought that he sees canals that bring water from the poles of Mars to the equator. And since then, you know, small little Martians, little green Martians filled our imagination. We know that water was running somewhere in the past on the surface of Mars, but to find running water now, it was a goal for many missions that sent to Mars, rovers and reconnaissance orbiter that orbiting Mars. And as we said, 2-3 weeks ago, NASA announced that running water was found on Mars. And for this, I want to present our 2 distinguished speakers, Bernard Freund, which is the chief scientist and senior explorer of ESA, European Space Agency, and James Graff of JPL, who is the former project manager of the MRO, Mars Reconnaissance Orbiter, which led to the conclusion that running water was found on Mars. So we want to begin with Bernard, please.
Thank you. Thank you. Yes, it's a pleasure to be here to talk about water on Mars, and in order to put in context some of the recent results, I'd like also to discuss what is the perspective, what we have learned before, because this is very important finding that was reported. Now, let's put yourself in space around the Earth, and what you see in orbit is a surface that is covered with water. Indeed, most of the surface of the Earth is covered with water, and we call the Earth a water planet. And indeed, water on Earth is linked. You have, for instance, this algal blooms population. It's linked also on the continent with life. But this is pure illusion. As we see, we don't know exactly where most of the Earth's water comes from. We know now it doesn't come from comets. Over the last 15 years, we have measured different comets, and we found that their deuterium to hydrogen ratio is very different from the one of the Earth. It's much more enriched in deuterium than the Earth. So the Earth, most of the Earth's water cannot come from there. Eventually, some of the Earth's water come from asteroids. They have the same deuterium to hydrogen ratio, or also some endogenous water. But if it's not true for the water, it's possible that most of the organics have been brought by comets or by carbon-rich asteroids. Now, where does this water come from? I can tell you we know the answer for sure now. This water comes because it's made of hydrogen and oxygen, and we know this hydrogen was created, like most of the hydrogen in your body, 13.7 billion years ago. Just a few minutes after the Big Bang, when the quarks recombine to form protons, and a bit of helium, but mostly hydrogen. And that's where the hydrogen from the water comes from. So problem solved. And where does the oxygen come? By the way, this is an image of the cosmic microwave background, because when these protons recombine with electrons 100,000 years after the formation of the universe, they emitted an intense radiation, which we can still observe now. And we have mapped with the Planck spacecraft that delivered this image. And from this, we can learn even about what happened during the Big Bang, the first 10 to the minus 30 seconds just after the Big Bang. But where does the oxygen of our water come from? This is a different story. This comes from the nuclear core of stars. And carbon, nitrogen, oxygen, this comes by different fusion reactions. And then those are ejected into space. And you can see, for instance, this image also of taken by Planck of our galaxy, how this gas and dust that contain carbon and oxygen from stellar nucleosynthesis is distributed. So this is the stuff we are made of. It was before in the Milky Way. So that's the second aspect of where water comes from. But of course, this was integrated in small bodies in the solar system, and at some stage, this was delivered to the Earth and to Mars. And we try to see, can we still see traces of this very early water in those planetary bodies? We find it also in stellar nurseries, in stellar formation regions all over. Water is found in small quantities almost everywhere. Even on the Earth, we found it, and we have found it on the Moon. But the Earth as a water planet, it's an illusion. Only the surface, this very tiny oceanic surface, is water. But the inside of the Earth is bone dry. And actually, we have found that when you measure samples from the interior of the Earth, from lava, or from the interior of the Moon, from lunar lava, it seems that the Moon is wetter than the Earth. So the Moon is a wet planetary body, and the Earth is a bit drier. And it's just because this water is going to the surface, and it's retained by Earth's gravity, that Earth is a blue planet. Indeed, we have also found traces of water on the Moon. With various missions, including Chandrayaan 1, we found some sign of hydroxyl, of hydrogen in the soil. And the US mission, L-Cross, with an impact, delivered ejecta which contain water and organics. So there is water on the Moon. De facto, there is water everywhere in the solar system. Even on our Sun, you can find in sunspot very hot water at 4,000 degrees. We have found water in the poles of Mercury, some deposits of water, and also some other compounds. We have also hot water in Venus, and we think that Venus, in its early story, had eventually much more water, but this was lost due to heating with greenhouse effect. Of course, water on the Moon we have covered. Mars, we had evidences of water, and we are going to discuss that and see the later discovery, but in different form. Ice, gas, liquid, we will have to review that. We have also signs of water in asteroids, in particular in Phobos, you can see that. And we have water as well on Titan. Not this. This is mostly methane and ethane. We have water in form of rock of ice, but it's raining organics on them. So we have water everywhere in the solar system, but in small quantities. Water on Phobos as well. And now let's come to Mars. Mars, a fascinating little brother of the Earth, where we have the processes that shape the planet, the interior, the volcanic. We have a big volcano there. We have a thin atmosphere. So if you make a spectrum of the atmosphere, you have also signature of absorption band of water. This was already discovered from Earth like more than 50 years ago. You have a surface where you have some things which are very reminiscent of some chaotic flows. We have an ice cap that we saw before. When we measured the spectrum of this ice cap in the poles, we thought it was CO2 ice, carbon dioxide ice, because most of the surface seems to be CO2. But it's not the case, as we'll see. And we had evidence of ancient fluvial liquid. Was it ancient fluvial water with some valley network? Or also you have some impact in some areas on Mars, which really seems to have occurred on the fluidized substrate. Today we can see signs of this water, also in clouds in the atmosphere and possibly in the caps. We see signs of erosion, and this is some indication of subsurface processes. This erosion seems to operate differently than on the Earth. It's more that you could have subsurface ice mixed with the soil that is being sapped. And then you have erosion making this way to cut down some of the island plateau. In some areas, you have chaotic terrain, so there are like some catastrophic erosion has taken place. Oh, these are images that were obtained by the Mars Express HRSC stereo camera. So you see, you have various discoveries in the history of the exploration on Mars, of where we have various evidence of the existence of water and ice. You see also sometime on these high resolution images in color obtained by the Mars Express HRSC, some deposit of minerals which have specific colors. You see also goodies, and our analysis of this data indicate that now Mars looks very dry, and it's very cold, globally. The question, was Mars also cold and dry very early, 4 billion years ago? Because it seems it has been cold and dry for the last 3 billion years. But that's globally. But are there some places where Mars is still active with liquid flows? That's an important topic also in the context of searching for life on Mars. But we believe that Mars had episodes. So Mars is also 4.6 billion years old, early in its history, 4 billion years ago, where there could have been some standing areas with water. And we see the signatures in the minerals that they have left from this epoch. And now you can just enjoy these beautiful views obtained from Mars Express HRSC, where you see the signature of water-bearing minerals, like the sulfates, in the Ebes-Casma Valley. You see how they are deposited and some of these goodies and their topography. Now you have also the signature of valley networks. So there have been a period where water was flowing on the surface in a kind of extensive way. Even in some areas, we have signs of catastrophic floods, like in this outflow channel. So there is a reservoir, possibly ice, in the subsurface, which is sometimes mobilized and gets catastrophic flows. You can also look a bit in detail what you see on Mars with some of these minerals deposit is very similar to what we see in some Earth's desert, where you see these salt washes, you see some sandstone, which are ancient riverbeds, which have it less eroded than their surroundings. Now, the recent studies from Mars Express and other satellites have shown also that there is a lot of ice present on Mars. And one of the surprises that we found is that some of this ice is relatively recent. And we have some areas in the poles where you have some stratified layers, here each corresponding to different climatic epoch where this ice was deposited and moving across the surface. Now, if you look with infrared eyes, in fact, with an infrared spectrometer, like the Omega spectrometer that we have on Mars Express, and you look at this polar cap, you see that the top is mostly carbon dioxide ice. But if you look through the cracks here, and the cracks are sometimes 2 to 3 kilometers deep, you realize that most of it is water ice. So this polar cap are 3 kilometers of water ice superposed by just 10 meters of carbon dioxide. So it's a lot of water is there. And this was confirmed also by a measurement taken by the JPL Italian radar on board Mars Express, and also by the Charade radar later, that there is extensive reservoir of ice, and actually not only in the poles, but also at some lower latitudes. And that's what we found also with the Mars Express. Very close to the equator and the tropics, we found glaciers, signature of glaciers, and we can date them, and we can see that they are just a few million years old. And we can attribute their presence to the fact that there are obliquity changes, and there are periods where all this ice moves to the tropic. So Mars most now is dry. It's the driest desert we could think. It's being explored to search for water and life ingredients, and that's how it looked like. And maybe at some stage, there have been some episode in the past, 4 billion years ago, where there was some lakes, precipitation. It was looking like this. But now we have found still some sign of subsurface water ice. For instance, the Phoenix mission scratched the surface and saw water ice and perchlorate present there at altitude. And also, so the Mars exploration rovers saw some sign of water processes there. And you can compare some of these strata. You see some spherules indicating some of this water episode. Like, for instance, now with curiosity, we see this strata and berries, for which you can also see the equivalent in some areas on Earth. Now, Europe is going to launch 2 missions to Mars, ExoMars 2016 in March next year, and also ExoMars 2018 with a rover that will drill 2-meter depths to see some of these organics and possible lives that would exist there. And the future is to determine whether life arose there, understand the climate, and prepare for human exploration. And clearly, its important theme now is to try to follow the water, to understand the implication for life, climate, geology, prepare for human, and then also look for the carbon. So this is my introduction. We have also in Europe filmed a version of The Martian, where we were also the actors, where in collaboration with JPL, NASA Ames, we tested instruments in the desert, that a ground-penetrating radar that can study surface water. We even drilled there. And that's what eventually we will prepare for future mission to Mars, based on the recent findings that my colleague Jim Graff is going to present us. Thank you. Oh, yeah. Please, we have the possibility to ask questions, and we have these ladies here that have some sheets where you can write your question, and then we will answer to them after the presentation from Jim Graff.
Thank you, Bernard. Those images were fantastic.
Thank you.
So I'm Jim Graff. I'm the former project manager for the Mars Reconnaissance Orbiter, and I'm going to be talking today a little bit about the mission, some of the science we've got from it, and then I'm going to highlight the discovery of water on Mars. I first want to thank my 3 colleagues, Rich Zurich, Dan Johnson, and Sarah Milkovich, for putting together this talk. Without them, that wouldn't be here. So let's first talk a little bit about the spacecraft and the mission to put you in context. First thing I'll say is that this is the Mro Spacecraft. That's a 3-meter diameter antenna that you're looking at there to give you a sense of size. The bus was built by one of our sponsors here, Lockheed Martin. There are 6 science instruments and 3 engineering experiments that are on board. Of the 6 instruments that are flying, 5 were sponsored by NASA, and 1, Charade, was sponsored by the Italian Space Agency. You can see the different bands in which they're operating here. Charade is a very low frequency radar, sounding radar. Mars Climate Sounder actually looks at the limb, and it's a microwave instrument. And then you have 3 in the visible range, or excuse me, 4 in the visible range. 3 of them, which is a context imager, HiRISE, and CRISM, all are what we call nesting. They all look at the same spot, and so that we can get a different view of the phenomena that we're looking at from each one of those instruments. I'm showing you this because I'm going to highlight data from the first 3 or 4 of these instruments. CRISM is an imaging spectrometer that comes from the Applied Physics Lab. The important thing for the water discussion is to look at the resolution that you have there. It's 18 meters across. That's about the best that they can get, and I'll come back to that later. HiRISE, which is the big imager, actually can get down to 0.3 meters sampling, which means it can resolve things at about a meter scale. Then we can talk about CHARAD, which again is the sounding radar, and CTX, which is the context imager. Its resolution is about 6 meters per pixel, so it can resolve about, say, 12 or 15 meter objects. So I'm going to leave this chart and just tell you it's a typical mission. We launched on August 12th, 2005. And those of you that can do the math realize that this year we celebrated our 10th anniversary since the launch. We had a Type 1 trajectory to get to Mars. It took us about 6 to 7 months. We arrived there on March 10th. And of course, that was one of those nail biters because the spacecraft goes behind the planet while it's thrusting, and you do not know if you've been captured or not until it comes out from behind the planet, and that takes 27 minutes. So that was a very intense period for all of us. And that was, of course, followed by another intense period, which is called aerobraking. Instead of remaining in a highly elliptical orbit, we brought ourselves down into a circular one, which was about 300 kilometers. And to do that, we used aerobraking technique, which is where the solar rays essentially interact with the particles of the atmosphere, slow yourself down. You're transferring your kinetic energy into heat. It can be very nail-biting also when you get very close to your final orbit and you're in constant atmosphere and with the chance of being very warm. After that, we started our primary science mission that lasted for about 5 years. I'm going to talk now about the science results. I'm going to break them into 3 different categories. One is ancient Mars, and ancient Mars means something that is 3.5 billion years or older. I'll give you 3 little examples of that. Then we'll move into recent, which really is the last couple of billion years up to about 10 years ago. And then we'll get into the present Mars, which is what I think most of you are interested in. So let's go and talk about the megabreccia that you find. Those are large rocks that were emplaced back billions of years ago. They've been exposed by meteorite creation on the crater, as you can see here. To give you a sense of the size, this image is about 200 meters wide, and the rocks you're looking at are about 10 meters across, the big ones. You also have CRISM, which is the imaging spectrometer, and that's telling you what the chemical constituents are of the rocks that you're looking at. On Mars Express, which Bernard was talking about, they have a great equivalent instrument called Omega. And whether you're using Omega or CRISM, you do find that all over the planet, in the northern and the southern parts, you find all of these hydrated minerals which were created in water. So billions of years ago, there was water, as Bernard was saying, on the planet in which these minerals were created. And then they were covered over, and then in the making of the craters, they've been uncovered again, and our instruments are finding them. This is one of my favorite ones. This is an ancient delta, and you can see the different colors on it, tell you what the different minerals are. There are clays in there, there are volcanic activity, volcanic rock, there's carbonates in there. They're all located in different areas. What the scientists know from this is there were 2 major epochs. The first one upstream is where they created the minerals, and then they got covered over. And then there was a second period of time, wet time, where they came and they eroded and dissolved the minerals, and then they flowed into the delta that you're seeing here. The delta is about 6 kilometers across, to give you a sense of the size of what we're dealing with here. So that we know that there was water, it was created, and then there was a second period where it actually drained out and formed this delta. With that, I'm going to move on to recent Mars. This is CHARAD. This is the shallow sounding radar, which means the radar pulses go and they penetrate the surface. And they can go down until they hit a reflective coating and then, or a layer, and then come back up. And in particular, we're showing you an image of what happens when you go across the northern poles. And you will see in just a second that we can actually look down at that cap and start looking at the layers that are contained in there. What does that mean when you look at the side view? Each one of these layers represents a change in the climate that's happened to produce it. The layer itself is dust and ice, and the thickness tells us how long it resided there before the next change in climate happened. So by examining this, we can go back in time and view the history. I'm also going to point out something here. Look at the escarpments and the cliffs that you're seeing here. These are rather dramatic, and I'm going to come back to those in a moment. So what does this mean? To give you a sense of the size, the thickness of this polar cap, and this is water ice, by the way, it's not carbon dioxide, is about 2 kilometers, and you can see the breadth here is about 500 kilometers. So each one of these layers that you're seeing represents a different significant change in the climate. Now let's fast forward to about 10 years ago when we first got out there. The context camera, which is a panachromatic camera, has a 35-kilometer swath, and we've used it to cover the planet. I think we've got about 80 to 90% of the planet now at 6 to 10 meter resolution. And it found this meteorite strike, and then we came back later and captured it with HiRISE. And HiRISE has 3 color bands in the center portion of it, and we were able to look at the meteorite. Then again, in 2008, we had context image here in June, and when we came back in August, we found that we had another meteorite collision, and HiRISE picked that one up later also. And we get up into the northern latitudes, when we start seeing these meteorite hits, we start seeing water ice come out. And that's what these images show you. You'll see that these sublimate quickly, and they continue until the dust that's entrained on them coats again the remaining ice, and then it stops the sublimation process. We know that because we've seen it here. There are 2 meteorite strikes on this. These photos cover about 15 weeks, starting in the upper left-hand side, and you'll see the bright water ice at the bottom of the meteorite crater, and then you see as you go across through time, it's coating up, and eventually we can no longer see the water ice. It's sublimating away. All right, so let's go to the present Mars, active ice. Now remember the cliff that I showed you in the northern regions. So we're going to come back to the northern regions, and this is a dramatic avalanche that we saw coming down one of those cliffs. The bottom left-hand side is the carbon dioxide, the highest layer, and you're looking straight down the cliff, and you're seeing an avalanche, and the red dust is about 200 meters wide, to give you a sense of that. And they think that the white jets that you see above are, again, another avalanche that's starting up. So you have one down below and another one starting up higher. What causes this? We don't really know. It could be gusts of wind. It could be there are elements that are warming up as we go from spring to summer, and that's causing expansion. It could be Mars quakes that are causing it. We don't know, but they're rather dramatic in looking at it. And some other images, plus they caught a couple of these here on the one on the left. Gives you a sense of the size and the scope of what's happening. Let's talk about the polar dunes. What you're seeing here is a false color image. They're each about 1.2 kilometers wide, and you're going from left early in the spring to later in the spring. And what you're seeing is this accumulation of dark spots on the ice, and we couldn't explain what was happening here. It took a while, and eventually the scientists came to the conclusion that what's happening is you have a surface like you're seeing now. The sunlight is going through the surface, it's hitting the ground, it's warming up the ground. Well, the CO2 is in contact with that ground, so it sublimates. The solid becomes a gas. and it starts building up pressure. You have the ground underneath, and you have this crust up above, and then you're starting to build up this pressurized gas. And eventually what happens is there's a crack up above, and the gas comes rushing out and comes up and spews out like a little geyser. And what you're seeing is the dirt particles underneath that are entrained in that gas as it starts coming out. As a matter of fact, there are images that show when you have a wind direction, you can show how all the particles are downstream of that. So this is a very unique process. It doesn't exist here on Earth. It's unique to Mars. Let's go to the southern hemisphere. Now, I was just talking to you about how these little geysers form. Of course, when the gas breaks through, you create erosion patterns in the ground. And the next season, when you come along, you have those patterns, and in particular, the carbon dioxide frost resides in here and creates these little spider-like entities. So each one of these was a previous geyser in the previous season. Wow. We also see in the southern cap these growing openings. The carbon dioxide is on the outside, and you're getting you're seeing the bedrock underneath or the water ice underneath, and this is a growing disk here, and we're tracking it as it goes. It's not just one; it's happening all over the South Pole. We're seeing this kind of sublimation that's happening. All right, let's get into the active atmosphere for a second. This comes from one of our instruments called MARSI. It's our weather instrument, and it tells us what's happening over the entire planet. It can view the planet in 1 to 2 days. So we can track the dust storms. 3 things I'm going to point out here. If you look at the South Pole, you'll see a massive dust storm. These images, there are 7 images here, by the way, created in March, 7 days in March. So that's what you're watching. So you'll see this major dust storm in the south here that comes along down in,
David.
Down here. Oh, it's not going now. There we go. You also see some regional dust storms up in the North Pole. And if you look at 31 degrees north and 331 west, which is the Ares 3 landing site that Bernard showed us, you'll see on the first image on the March, I think, 19th or so, there was a regional dust storm that was hitting that spot. So the Ares 3 landing site that's on Mars would have had a dust storm hit it right through there, and this particular week nailed it. Let's go on and talk about some other features that are dynamic presently on the surface, and that is the dust devils that you see. Now, a dust devil is normally about 70 meters wide, but it can go up 20 kilometers into the atmosphere. And as it goes along the surface, it scours the surface and it sucks off the existing iron dust, leaving behind dark tracks that show the bedrock underneath. And that's what you're seeing here. These are the dust devil trails that are residing there. Okay, let's go and talk about the present now, and we're going to talk about the active surface. Now, I've been talking about natural events on Mars, but there is some activity on Mars that, in fact, it was not there, that, in fact, humans added to it. So the first thing I'm going to point out is this is the landers. This is our rogues gallery of the landers that we've been able to observe. You'll see in the upper left-hand side is Pathfinder. You can't see the Sojourner rover. It's too small to resolve, and it may have wandered out of this area, so no one knows where that is right now. When you look at the right side, you'll see that's the Opportunity landing site, and that was essentially a Martian golf shot, which was a hole-in-one. When it landed, it rolled. It had its airbags, and it rolled right into the crater where there was bedrock. And the bottom are the Voyagers, or the Vikings, excuse me. There's one other that we've been able to identify, and that is Beagle 2. This January, a team that had been scouring all the images actually believes they found Beagle and some of the heat shield, which will give the Brits a little bit of closure, hopefully, knowing that Beagle 2 actually did get to the ground roughly intact. Some things went right. What went wrong, we don't really know at this particular point in time. They may know. Okay, let's move on and talk about Victoria Crater, other dynamic features that are going on there. I'm going to rush through this, and actually I'm going to skip through this if I can and get over to Gale Crater. This was Curiosity coming down, so we actually captured it with the high-rise imager as it was descending on the parachute. And then, of course, we have what we call the crime scene image, where you can see there's Curiosity, and then in the upper right, you see a blow-up of the sky crane where it landed, and that's the contamination of the site from the jets there that you're seeing. And in the lower left, you're seeing the parachute and where it came down. Now, this is the landing site over here, and these are the tracks of Curiosity. It's about 2 to 3 kilometers, and Curiosity is located over there. And so we can track, and we can help the drivers know exactly where they want to go. This is an image that's pretty dramatic. It gives you a sense of the daunting task that you have once you arrive at the surface. The drivers really need to know what's out ahead. In case you can't see it, this is where Curiosity resides at that particular point in time. So it gives you a sense of the complexity that we need, not only the boots on the ground provided by the rover itself, but we need the eye in the sky to tell them where to go. Scientists didn't know if the major sand dunes were fossilized on the planet. They didn't know if they were set there and they had never moved. We followed for 3.5 years this sand dune in Herschel Crater, and it's moved a couple of meters, plus the whole top has changed. And that gives us a sense that the planet is dynamic, it is continuing to move, and we're seeing dust devils, we're seeing the sand dunes move. It's a very interesting planet. Okay, let's get into slopes. This is not water. These slopes were essentially dry avalanches that came down from the edge of the rim of the crater itself. What you're seeing in here are 2 different types of streaks. The most prominent one is the dark streak, which are the most recent. So the avalanches has come down, and they've taken off that little crust of red dust that was there, and it's showing the bedrock. Where the lighter streaks are, and you can see them up here and here, those are older streaks that have come through that are starting to get coated again. We actually see thousands of these streaks all over Mars. This one was very interesting. In the lower left, we have the context imagers. We come back to different sites, and all of a sudden we found something had changed. So we went back with the high-rise imager, and we looked again, and of course, we believe up where the arrow is a meteorite hit there that probably caused this avalanche here. Now, let's get into the water. This is what I think you've all been waiting for. What I'm showing you here is 7 shots. They start in the spring, go through the summer, and starting into the fall. In the spring, I'm going to let this run so you can take a look at it. In the spring, there are no recurring slope linii, the RSLs, as the scientists like to call them. But they come very prominent in the summertime, and then they drift off again. They only appear on slopes that are about 20 to 40 degrees. They only appear on what we would call the sun-facing sides of the craters. In other words, the equator-facing sides. They appear in the north and in the south. What are they? That's the big question, okay? So we see them. Remember, I told you I was going to come back to the resolution issue with CRISM. On high-rise, we can see these slopes because they vary from about 0.5 to about 5 to 10 meters. But a CRISM spot size is about 18 meters. So it's been very difficult to look at this and be able to eke out what the chemical constituencies are here. But they were able to do it in 4 different locations around the planet. They were able to overlay a CRISM image. And what they found were the perchlorates. They found hydrated salts in this flow. It's a briny flow. What does perchlorate do when you put it in water? Well, first of all, it drops the freezing point about 70 degrees, so you're minus 70 degrees C when you hit that freezing point. It also delays and slows the evaporation so that liquid water could stay longer on the surface. It also is a getter, and it brings in the humidity in the atmosphere, which it plays into some of the ideas of where the water's coming from. And I'll talk about that in a minute. So most of the recurring slope lineae start in the bedrock, and you can see some of them back in here, all the way back up to here and come flowing out. The question is, I'm sorry, there's an important factor I almost omitted. They're not seeing the water here. We don't have an imaging spectrometer that's going down and saying, oh, I see fresh water. What they're doing is seeing the hydrated salts that are left there. Those images are seen only when the RSLs are there, or it's a very high concentration. They see the high concentration when they're there. When they're gone, they lose it. So they see a correlation between the two. So what they think is happening is you're getting a seepage of water out from under the bedrock that's going underneath the ground and dampening the surface. And entrained in it is this brine, and the water eventually evaporates, leaving the high concentration of the brine. Now, one of the things is we have an equator crossing time of 3 p.m. That's about the hottest you're going to find there. It can get up to, some of these craters can get up to about 300 degrees Kelvin on a very warm day. And so you see the seepage coming out during that period of time, and it's evaporating. So what one of the questions are that we have is, what would we see if we were at a different time of day? If we were at, say, noon or 11 a.m., would we actually see the water? Is the water actually evaporating at the hottest time of the day, so we're only seeing the salts? That's a question for an additional mission to come along and take a look at. What are some of the other sites that we've seen water? Here's the Valles Marineris. You can see a couple of sites here, and here's some close-ups of it. And then here are 4 shots showing you additional RSLs appearing also in roughly the same area. So in the Horowitz crater, they did capture a pixel on top of one of these, and you can see on the right is the spectra that they've seen for these perchlorates in the laboratory, and you can see in the center is the one they actually got on this 1 pixel here. Give you a sense of that. So Mars is dynamic. It's constantly changing. We're seeing landforms change. We're seeing what we believe now to be water flowing out through the bedrock and onto the sand. And it's a fantastic place to study, and perhaps sometime we'll get to go there. So I think I'm going to leave you with this final image, which to me embodies the Martian development. What you're seeing here is this picture of Victoria Crater, and as we focus in, you will see the Opportunity rover in the upper left-hand corner. Amazing. What does this show you? It's a couple of things. First of all, you need the rover on the ground to be able to do the in situ measurements and to get up close to the rocks. You need the eyes in the sky to be able to tell the rover where to go, but also to take the science investigation results that rover has created and apply it over the entire planet. So that's the end of the talk. I appreciate it.
Bravo.
Thank you.
Amazing. Wow. Bravo.
Thank you, Bernard and James. And now we collected some questions from the audience, and I'll represent them to the speakers. The first one is from Dekel Shachar, but it's not addressed. So, how the correlation between Earth dunes to Martian dunes can present the atmosphere state of Mars?
I can't follow it. It's really hard to hear.
Okay.
The correlation between Earth dune and Martian dune. So how is it linked with the atmospheric
The
properties?
correlation between the dunes, yes.
Well, clearly, as you know, the atmosphere of Mars is much tenuous than the Earth. You know, Earth is 13 millibars. Mars is 7 to 10 millibars, so it's less than 100 times less. But still, this atmosphere is enough to drag, lift dust and form dunes. And well, in your movie, you can see them move. So over what period of time was that?
That was over a 3.5-year period that the dune was moving. It moved about 2 meters. So it's not perhaps as dramatic as you might have on Earth, but for Mars, that's quite a maneuver. They've seen dunes that are 200 meters high moving across the surface.
And sometimes you have an even period where you have some local dust storms, where we have seen these devils.
Yeah.
But sometimes you have the whole region is being covered by dust, and at some period you have even global dust storm. And that's where you don't want to enter the atmosphere.
That's right.
Yeah.
Thank you. The next question is from Siddharth Pandey from UNSW Australia, and it's addressed to Bernard. I think that James can answer also. Any discussions, strategies to sample at RSL sites?
I can't follow what you're saying.
Yeah.
Any discussions on strategy?
Well, it's one of our priorities after the mission we are conducting now to have a Mars sample return. Mars sample return for search for life, but also for understanding the history of Mars.
I think Bernard has said it very appropriately. We are looking at Mars sample return. Where you go and sample is an issue that the scientists have to determine as we go forward. One thing to keep in mind is we're talking about slopes that are 20 to 40 degrees, so it's not easy to get to those locations. You have to develop a whole technology that enables you to get up there and be able to take the sample of those RSLs. So getting to them is an issue that we have to contend with, and you may not want to do it with the first Mars sample returned.
Yeah, we are going to try to explore with rovers some areas we have identified because we believe that there were areas of standing water, or like the Morse valleys, and you have some mineral deposit. It would be interesting to monitor if there are some of this still present activity.
Yeah. But you have to realize the announcement that came out just a couple of weeks ago is right now in the forefront of many of the investigators' minds. So they're going to be thinking about, shouldn't we really go here? Shouldn't we go and see what these brines are really like? So I think it is going to be one of the hot topics for the next science teams to discuss.
The next question, addressed to James, is Kartik Chand from Aerospace India. How are you planning to analyze the RSL at the rover can due to Planetary Protection Act?
Oh, this is a good one. First of all, the rovers that we have on the ground can't get to the RSL, so we're going to have to, as we discussed previously, talk about a mission to go there. When we go there, we always are working hand in hand with our planetary protection organizations, whether it's in ESO or the United States, to make sure that we minimize the extent to which we take our bacteria there and our life forms. We certainly wouldn't want to put them in any way, shape, or form, expose them to.
Yeah, so there are different aspects of French protection. The one, if you search for organics, for instance, you don't want to bring them from Earth. If you search for life as well, so that's a kind of scientific protocol. But if you bring back samples, it's even more, because you want also not to endanger the planet. So it's a very strict regulation. Now we have to make the case whether these brines are livable. I'm not sure. Well, Dead Sea, it's even more salty than the Dead Sea.
Yeah.
Seems like a nice place. But there are some experiments which are conducted, for instance, in some of the saline part of desert, where you have also very big
The
salt
Atacama
concentration.
Desert has had some,
And there are
it's
some
very dry and has had some bacteria survive there.
Yeah. So who knows?
Which leads to the next question, the same issue, it's anonymous, and to both of you. Is there a form life on Earth that we can expect on Mars? And is it likely to be survive and even thrive?
Expect or even export. Wow. Exporting life to Mars. But first, expect, well, they must survive to extreme conditions. So you have on Mars, extreme dry condition overall.
Yeah.
Okay, but you have also low temperature. You have also UV radiation. For instance, we have made experiment in the laboratory. If you put some amino acid on the surface of Mars, this is killed in 30 minutes because ultraviolet penetrates through the atmosphere, the ultraviolet at 200 nanometer. Now, if you are on the subsurface, this could isolate you, but we have found that there is a peroxide, perchlorate, also these strong oxidizers, but below the surface, there could be niches.
It could be.
But now, what about exporting? Yes, actually, it will be simpler
Well, we don't.
to bring life there than to find life, but we don't want to do that.
No, I don't. We don't. The intent is not to export any of our life there, is to make sure that we go there and we'd like to, if we find life there, we want to make sure it's not the one that we brought there.
Yeah.
We want it there to be real Martian.
Yeah. Of course, it would be very fundamental if we found life on Mars which is not linked to life on Earth. There may have been possibilities that have been exchanged between those planets, and some form would have made them and retreated in some niches. But the most interesting question is, did life happen in another place in a different way? And this would be a huge, for knowledge and also for society. Now, clearly, you don't want to kill the object of your study in that case.
Which is the last question, which is
sorry.
an overall one. Where can life be supported outside Earth?
Oh, well, we do it on the International Space Station already.
Yeah.
We'll do it on the moon.
Moon, the village.
On the moon village, we support. And there we are going to learn how to maintain a community on Mars, which is not going to, which has still to preserve some areas on Mars which have to be protected before we know all the aspects of life.
Yeah.
And then, okay, I don't know, should we make Mars habitable? That's another question.
Oh, terraforming.
Question for you.
That's a subject of another whole nother session.
Yeah, but on the other hand, based on what we have found, that there's a lot of reservoir of subsurface ice.
Yeah.
Terraforming could be, in fact, it's not that easy. Huh? We are talking about putting some greenhouse gases on Mars, and after a few hundred years, you could release enough water in the atmosphere. Then you can start to have an additional greenhouse where water could be made to flow, to be available on the surface. But it's okay.
The real problem with any sort of terraforming, so to speak, is the inability of the gravity to hold on to the hydrogen molecules as they're lost into space. And so you need a way of continuing to refresh them. So it'll be very interesting to see what happens in the future.
Yeah, I mean, those that terraform Mars, they bring back Mars to the original state, because maybe 4 billion years ago, Mars was covered with standing water. So in a sense, it's very moral. Go back, and the value of life is positive. So let's bring life in other places that can host it, but without destroying life that would be present there, or preserving it.
Okay.
Okay. Thank you, Bernard and James.
Okay.
And thank you for having us. And enjoy the last day of the IAC.
Okay.